Today in BE 110, we'll turn our attention from the universal governing equations of continuum mechanics, the conservation laws, to the specific equations that describe the mechanical properties of particular continuum materials, and these are called the constitutive equations. Constitutive equations describe the mechanical properties of specific materials, in particular by providing an equation for the stress as a function of a kinematic quantity. They're so named because the constitutive properties, the mechanical properties of a material, depend on its physical constituents, its structure and microstructure. In theory, the constitutive equations could be derived from more fundamental principles found, for example, in statistical mechanics and thermodynamics. But in practice, these also require idealizations, and for real materials, especially in biomechanics and biophysics, we need to use experimental tests. It's important to realize that constitutive equations are idealizations, they're approximations of reality. And the validity and accuracy of the idealization doesn't depend only on the material. It also depends on the situation or physical problem that we're trying to solve. For example, it can depend on the scale of the problem. If we're interested in modeling the flow of water around a ship, then this could be a very different approximation than modeling the flow of water in microchannels. It also depends on the physical problem that we're trying to solve. For example, the flow of air in the lungs or the flow of blood in the blood vessels can be accurately approximated as an incompressible flow. Blood and air for those problems can accurately be approximated as incompressible fluids. But if we were interested in the way ultrasound waves propagate, which is also a problem that can be solved with the equations of continuum mechanics, then we couldn't use the assumption of incompressibility because, in fact, the very propagation of sound waves depends on the fact that fluids like blood and air are slightly compressible, and the difference between the ultrasound densities that we see in the lungs and the blood is dependent on the difference in the density between the air in the lungs and the blood in the vessels. It also depends on the loading conditions. For example, in many engineering problems, when the material is under the working loads, then we can assume that the material is elastic and frequently linear. But those same approximations and equations wouldn't be valid if the material was under failure loads. So we use certain constitutive equations for design conditions, but we have to use different constitutive equations to understand failure conditions. Now, as we know, there are different types of continua that are all governed by the universal equations of continuum mechanics. The main differences between solids and fluids is that solids can sustain a shear stress indefinitely without flowing, and they usually have some defined, unloaded, or original natural state. Fluids, on the other hand, cannot sustain a shear stress indefinitely without flowing, and they have no particular unloaded natural or preferred state. As you know, fluids can be liquids or gases, and they differ mainly in their density and compressibility. Fluids tend to be more dense and less compressible. Gases are less dense and more compressible. In biomechanics, we frequently encounter materials that actually have combinations of solid and fluid-like properties. So our first example of a constitutive equation will be the constitutive equation for a Newtonian viscous fluid. In a Newtonian or linear viscous fluid, the shear stress tau is linearly proportional to the shear rate gamma dot, and the constant of proportionality is called the viscosity mu. Thus, for a linear viscous fluid, we can write tau is equal to mu gamma dot, where mu is a constant. But this equation isn't a constitutive equation, because a constitutive equation must give us all of the components of the stress tensor. So in general, a linear relationship between the shear stress T and the rate of deformation tensor D will look like this. Tij is equal to minus P delta Ij plus Bijkl times dkl, where P here is the hydrostatic pressure, which is a function of density and temperature, and this quantity here, this fourth order tensor Bijkl, which can also be a function of density and temperature, is the fourth order coefficient tensor of coefficients relating the stress to the rate of deformation. Now, why did we separate out the hydrostatic pressure P? Well, that's because when a fluid is not flowing, dkl, the rate of deformation, is equal to 0. But there can still be stress in a non-flowing fluid, and that stress is the hydrostatic pressure minus P. So therefore, the stress tensor in a fluid that isn't flowing would be minus P on the diagonals, or Tij is equal to minus P delta Ij. Now, since the pressure is unknown in this formulation, we need an extra equation or condition to find it. There are two possibilities for defining that extra condition that can be used to solve for the hydrostatic pressure. The first is incompressibility. So in an incompressible fluid, we have the extra constraint or equation from conservation of mass that since the density is constant, the divergence of the velocity vector is equal to 0. The other possibility is that the fluid is compressible, or at least not specifically assumed to be incompressible. In this case, we need a relation for the pressure, typically as a function of density rho and temperature, written here as theta, so as not to be confused with the stress, capital T. This is an equation of state, and a perfect example of an equation of state is the ideal gas law, which states that P equals rho r theta, where r is the gas constant. So now let's turn our attention to the fourth order tensor Bijkl. Now, since we've assumed that the relationship between stress tensor and the rate of deformation tensor is linear, this means that the components of Bijkl are constant, but there are 3 to the power of 4 of them, meaning there are 81 constants. Now, we can simplify this somewhat. Considering the symmetry of the stress tensor T and the rate of deformation tensor D, we can write that Tij must equal Tji, which means that Bijkl must equal Bjikl. Similarly, from the symmetry of D, we can write that dkl equals dlk, therefore Bijkl is equal to Bijlk. So this has the effect of reducing the number of independent constants in Bijkl from 81 to 36. So think of that 36 as being 6 squared, namely there are 6 different components of the symmetric stress tensor and 6 different components of the symmetric rate of deformation tensor. So there must be 6 by 6 independent coefficients. Now, to simplify Bijk more than this, we must consider material symmetry. So material symmetry describes the properties of the material as a function of orientation. And the simplest case of material symmetry is isotropy, and it applies essentially to all fluids except to some very unusual fluids like liquid crystals. An isotropic continuum is one whose material properties are invariant under the group of all orthogonal transformations. In other words, an isotropic material is one in which the result of a specific mechanical test would be unchanged by any rigid body rotation or reflection of the material. Put more simply, this means that the properties don't depend on which direction you test the material under. Now, it's easy to think of solid materials where this could be the case. Think of a piece of wood where along its grain a property would be different than against its grain. But it's very hard to think of a fluid that would have this property. And in fact, it can be proven that for true fluids, it's the only possible material symmetry is isotropy. Those unusual fluids that do have anisotropic materials, it's actually a result of some solid-like behaviors. So in general, any fourth order tensor that is isotropic can be written in the following form. Bijkl is equal to lambda times delta ij delta kl plus mu times delta ik delta jl plus delta il times delta jk. So these are the components of the fourth order tensor that is invariant under all orthogonal transformations. What that means is that we actually have reduced the number of independent constants when the material is isotropic in our fourth order tensor from 36 to 2, being lambda and mu. Hence, going back to our constitutive equation, we can now substitute this form into Bijkl into our constitutive equation for stress in a Newtonian viscous fluid and obtain the following equation. Tij is equal to minus p as a function of rho and theta, the temperature, plus lambda as a function of rho and theta times dkk, trace of the rate of deformation tensor, all times delta ij, plus 2 times mu, also a function of density and temperature, times dij. Or, writing this in direct notation, the stress tensor T is equal to minus p plus lambda times the trace of d, all times I, the identity tensor, plus 2 times mu times the rate of deformation tensor. This is the equation for a Newtonian viscous fluid. And lambda and mu are the two material constants that describe the physical properties of the fluid. Now there are some special cases. One special case of a Newtonian viscous fluid is an incompressible Newtonian viscous fluid. In this case, the density rho is constant, which gives us that the divergence of the velocity vector v, or the trace of d, is equal to 0, and that's this term here, so therefore the constitutive equation for an incompressible Newtonian viscous fluid simplifies to Tij equals minus p times delta ij plus 2 mu times dij, or in direct notation, T equals minus p times I plus 2 mu times d. Note here that the pressure P is no longer determined by the constitutive equation at all, and it's determined solely by the incompressibility condition and the boundary conditions imposed on the equation of motion. So in practice, in an incompressible fluid flow, the external pressures determine the hydrostatic pressure P. Another special case is the ideal fluid, which means that it's both incompressible and inviscid. Inviscid means the viscosity is 0, so that just reduces to Tij is equal to minus p delta ij, or T equals minus p times I. So now let's look at an example of stress in a Newtonian viscous fluid, an incompressible Newtonian viscous fluid, under simple shear flow. So remember that a simple shear could look something like this, where here we have velocity in the x1 direction, varying in magnitude as a function of x2. So v1 is equal to v1 of x2, and does not depend on x1 or x3, and v2 and v3 are 0. So the only non-zero components of the rate of deformation tensor are d12 and d21, which are equal to 1/2 del v1 del x2 plus del v2 del x1. This term's 0, so that leaves 1/2 of del v1 del x2, with all the other components of the rate of deformation tensor being 0. Writing again the constitutive law for an incompressible Newtonian viscous fluid, we have Tij is equal to minus P delta Ij plus 2 mu Dij. So T11, T22, and T33 is simply minus P. T21 and T12, which are labeled tau, will therefore be equal to 2 mu times D12, where D12 is 1/2 del v1 del x2, so this leaves us mu times del v1 del x2. The other shear stresses are 0. So this component of the shear stress, tau, is the only shear stress in the problem. Del v1 del x2 is sometimes called gamma dot, the shear rate, and hence in this problem, for an incompressible Newtonian viscous fluid, we can write tau equals mu times gamma dot, just as we originally posited before we derived the general governing equation. So mu is called the viscosity, and for a Newtonian viscous fluid, the viscosity is constant. In this exercise, consider a cone and plate viscometer with an outer radius r that is spinning with angular velocity omega. The spinning cone makes an angle theta to the stationary plate. The torque T applied to the plate by the fluid is measured by the device. For this problem, you can assume that the circumferential component of the velocity, v theta, is only a function of z, where z is the axis of rotation. And for an incompressible fluid, we can show that v theta is a linear function of z. Derive an expression for the viscosity mu in terms of the torque, radius r, angle theta, and angular velocity omega. So what was your solution? Was it A, t sine theta over 2 pi omega r cubed, B, t tan theta over 2 pi omega r, C, 3t tan theta over 2 pi omega r cubed, D, t cosine theta omega over 2 pi r, or E, t omega r squared over tan theta? First, let's calculate the shear rate gamma dot, which is dv theta dz. Now, v theta is a function of r, so therefore this can be expanded as del v theta del r dr dz, which is del omega r del r times dr dz, or omega dr dz, and since dz dr is tan theta, that is omega over tan theta. Now the shear stress tau is mu times gamma dot, therefore tau is mu omega over tan theta. Now the torque is the integral of that shear stress over the area times the moment arm r, which will give us the double integral of tau r times r dr d theta, or 2 pi times the integral from 0 to big R of tau r squared dr, which is 2 pi of the integral from 0 to r of mu omega over tan theta, which are all constant, times r squared dr,
which is therefore 2 pi mu omega over tan theta times the integral of r squared, which is r cubed over 3, evaluated between 0 and capital R as capital R cubed over 3, gives us that the viscosity mu is 3 times the torque T times the tan of the angle theta divided by 2 pi omega R cubed, which is
Let's consider the units of mu. So the units of the shear stress are units of force over area, so force over length squared, and the units of shear rate are length over time, so 1 over time, which means that mu must have units of force times time over length squared, or Newton seconds per meter squared, or Pascal seconds. In some texts that use CGS units instead of SI units, you'll see the term poise, and 1 poise is 10 Pascal seconds or 10 Newton seconds per meter squared. We'll also sometimes see the term kinematic viscosity. The kinematic viscosity nu is defined as mu, the viscosity, divided by rho, the density. Now, viscosity typically increases with temperature in gases and decreases with temperature in liquids. As a few examples, the viscosity of air at 20 degrees Celsius is 1.8 by 10 to the minus 5 Pascal seconds. The viscosity of water at 20 degrees Celsius is 1.0 by 10 to the minus 3 Pascal seconds, 50 times greater. The viscosity of blood plasma at 37 degrees Celsius is only a little bit greater than that of water at room temperature, 1.2 by 10 to the minus 3 Pascal seconds. But the viscosity of whole blood is not a constant. Unlike blood plasma, whole blood is a non-Newtonian fluid. The presence of the red blood cells makes whole blood non-linear, and it's sometimes referred to as a shear thinning fluid. So the faster the blood flows, the higher the shear rate, the lower the apparent viscosity. So the viscosity is no longer a constant, it depends on the shear rate. And so a Newtonian viscous fluid is not such a good approximation for whole blood under many conditions. Next, we'll go on to introduce the constitutive equations for linear Hookean elastic solids.